Thank you very much. Good evening, everyone. It's my great pleasure to be here, and I really want to thank the conference organizer to have our paper on the program. This is joint work with David Brown, my colleague at Madison, who is also here. So the paper has some very simple idea. So we start with this observation that most mutual funds belong to a family, and fund performance is a joint outcome of the individual manager's talent and the resource of the fund family. So there's some empirical evidence on that. For example, this paper by Bax in 2003, he actually reported that maybe up to from 50 to 90% of the performance is actually attributable to family instead of individual manager. But the related observations that also funds within the same family are subject to correlated non-systematic shocks. We will also present evidence on that, and there's a paper by Elton, Gruber, and Green. They also document that returns of funds within the same family are more correlated. So I think the phase effect somehow indicate that the performance, behind the performance, there's a common skill that generate this performance. But the second observation would imply that there's also common noise or correlated noise in the fund return. Then the implication is very simple. If we want to measure the skill of the fund, which would be a composite skill of family resources and the manager skill, you should look at fund in this family setup, not just look at the fund in isolation. So performance evaluation should be based on the performance of all the funds within the same family. So our research question is then how do you put all these things together to form the most effective evaluation of the fund skill? So we thought this is a natural setup for building a continuous time-based learning model, but with multiple funds. And the related question is, what are the effects of family performance? What are the effects of family performance on the assessed skill of a member fund, and what drives those effects? And then we also asked two empirical questions. Is the hypothesized family effect, what it means that the effect on the common skill, the skill and noise, are they observed in the data? And then do invest use the manager performance, family performance information in a way that is consistent with optimal learning? And for that, we look at the fund flow sensitivities to both fund and family performance. So here's the brief overview of the theoretical result. From our theoretical model, we actually highlight two competing effects of family performance on the evaluation of a member fund. Just as I alluded to earlier, there's a common skill effect. This is positive, meaning that if the family is doing well, this should raise your evaluation of a particular fund in the family. But there's also a common noise effect, and this actually go in another direction. And the determinants of the overall effect is then, in a steady state, can be pinned down to three factors. One is the correlation of changes in the unobservable composite skill. I will make it clear later what we mean by composite skill. And then the correlation of unobservable noise. And then also depends on how many funds you have in the family. These are results in a steady state. In a non-steady state, then things are more complicated because the initial uncertainty hang over, right? Things are more complicated. But the main results, like the composite statistics, the effect of these two correlations on the evaluation are still the same in a non-steady state. But we also show that in a non-steady state, you don't really need to have time-varying ability to generate the common skill effect. Actually, uncertainty about the family skill is sufficient to generate the common skill effect even when the skills are constant. In a steady state, of course, if things are constant, then all the uncertainty disappear in the long run. We also have some empirical results. We show that family effect does exist in the fund return in the sense that we find higher correlations in the estimated alphas for funds within the same family, and we also find higher correlation in the residual return. And surprisingly, we also find the patterns of mutual fund flow are very much consistent with this optimal learning model would predict. they are increasing the fund flows to a member fund, the sensitivity of fund flows to the family performance. They are increasing in the correlation of estimate alphas, which is used as a proxy for the correlation of the skill, and decreasing in the correlation of estimated residuals. And we find this pattern are stronger in a bigger family, just as the theory would predict. For clearly, this is a paper about mutual fund performance evaluation, and there's a very long literature on this topic. But traditionally, the evaluation is usually take the fund and view this fund in isolation. More recently, there are several papers, like starting with Pastor Stumber and also Jones, Schenken, and Cohen, Kova, Pastor. They say, you should bring in some other additional information, like the whole cross-section of mutual funds, or the other funds that have similar holdings, bring those information into evaluation of a particular fund. And this will improve your evaluation. And the idea of this paper also related to the relative performance evaluation literature. Like in the 80s, Armstrong, Gibbons, and Murphy, they showed that if the noise are correlated, if you use both the peer performance and compared to the particular agent's performance, this will improve your inference, right? And then induce better effort. But they basically just consider the common noise effect. And in our model, we have both common noise and common skill effect. And this paper, of course, is also part of the mutual fund flow paper. And there's again, quite long literature. But one that's most closely related to this paper is like Beck and Green, and my paper is Dangl and Zechner. These are all based on learning, right? It is, so we work in an environment like a Beck and Green model works. So let's just talk about the model. So this is basically an extension of Dangl-Zechner model in 2008. We just extend this one fund model to a multi-fund model. There's like the fund return that is driven by, of course, the fair rate of return is driven by like exposure to the systematic risk. And this is like risk-free rate plus the price of risk multiplied to the exposure. But then there's also this additional alpha generated by the skill. And then minus phi, right? And this is like a vector of funds. So you could observe them. Then this exposed to the systematic risk factor, WMT, and then the non-systematic risk. Here you see that the non-systematic shocks are correlated, which is then described by the BB prime matrix of correlations. Now we have to specify how alpha is generated. Alpha is generated by the ability, theta IT, and of course you have to take some idiosyncratic risk in order to generate alpha, and this we incorporate the assumption of Berg-Green. There's a discombinant scale, and especially the return to taking idiosyncratic risk is declining, especially if the fund is big. And now what's special is here is that we assume the fund skill is a linear combination of family skill of family resource, and this is theta FT, and then the individual manager's ability. Beta I here then just measures the degree of reliance on family resources. Then we specify the dynamics of the true skill, which is following this equation. And because they share this common component theta F, they are correlated, right? So this equation has three special cases, right? One special case is as a case 0, the exposure to the shocks are 0, then you just have constant skill. And then you could also have this random walk skill process where you basically have the k equal to 0. And then you could also have the, we talked about these three different cases in the paper because we do think that managerial skill, portfolio management skill, is not like our skiing skill, that once you got it, you will never forget it. The portfolio manager are playing with the market. Market is always changing over time. So the portfolio manager skills, some strategy work one time, but not in the future. So they do have some time variations. So here, then we can define instantaneous correlation of the composite scale. This is, of course, given our assumption of a linear combination scale. So this is basically beta I, beta j, that's the common component in the scale set, times the volatility of the family scale squared, divided by this omega I hat, omega j hat. These are basically instantaneous volatility of the composite scale. So this parameter seems to be, turn out to be very important because it captures two things. The first thing is to what degree you the fund rely on the family resources. And the second thing is that it captures the variability of family scale relative to the individual manager scale. Now, the information is that you don't really observe the theta, you just observe the return, and you observe the risk they take, you observe the shocks to the market, but you don't observe the idiosyncratic shocks. So you have basically this observation equation, which is driven some unknown theta. Now, of course, then we just use the Kalman-Bucy filter, which is very well established in this setup. Then we find that investors believe if they start with the normal, then it's continue to be normal. And the belief about the mean scale is also mean reverting, and it can be described by equation 7 here. There's a mean reverting component, but also there's a component which summarizes the response to unobserved performance, right? And this response is then summarized by this sensitivity matrix, and it can be decomposed into this conditional covariance matrix and the correlation matrix, right? Inverse of the correlation matrix. So here, then this is just then we just do this updating, and we actually consider for the special case of random walk and constant scale, we can solve the VT in closed form, and otherwise we just solve this Riccati equation numerically. So just to give an intuition of cross-fund learning, here is supposed to be taken simple case. You have a homogeneous fund, meaning that the two funds look identical. They have same beta, same omega, and then we have this covariance matrix, and then the sensitivity matrix can be derived. Just write down this very easily. You can see that the first element of this matrix basically describes the sensitivity to the fund's own performance. And then the second element describes the sensitivity to the second fund's performance. And you can see that this, if you take the homogeneous fund, the sensitivity to your own performance is always positive. But the cross sensitivity, which is sensitivity to the estimate of a fund's composite scale in response to the other fund's performance, can be either positive or negative. Depends on how strong is the covariance and how big is the correlation of the noise. Now, for two funds, we can, if you take a steady state, meaning that when the covariance match converge to a constant match, and then you can derive the sensitivity metric is just described by these equations, where the omega hat is the volatility of the composite scale, and lambda is the correlation of the scale I just described. Basically capture like the co-movement of the scale. And rho is the correlation of the errors here, right? So this equation pin down the sensitivity matrix. And you can have some easy comparative analysis. If you set lambda equal to 0 and rho bigger than 0, you will just see the cross sensitivity negative, which is a pure common noise effect. Now, if you shut down the noise effect, set rho equal to 0, lambda bigger than 0, you will just have pure common scale effect, right? If the two are equal, then there's no spillover effect. And if one is bigger, lambda is bigger than rho, then you have overall a positive spillover. Otherwise, you have overall a negative spillover, right? And if you just take the ratio of these two, then omega hat drop out. You just have lambda and rho determine everything. Now, we could look at more like bigger funds, because the number of funds matters, because that determines how many signals you get. about this skill, right? So for n-fun family, you could also derive this sensitivity metric if the skill are random walk. You could also solve the sensitivity matrix in closed form, and basically the main result. I won't bother you with this a lot of matrix operations, but the basic result is that the two fun result carry through to the n-fun case. But the additional result is that the number of fun really matters. If you have bigger family, then the effect of this correlation on the influence is going to be strengthened. It's going to be bigger. Okay, so here's the graph where I plot the ratio of the sensitivity to family performance relative to the sensitivity to the own farm performance, and you see that this is showing the impact of rho. For you, if you fix the lambda to be 0.2 and you increase the rho, increase the correlation of errors, then the sensitivity to the family performance actually go down and become negative. Otherwise, if you reduce the rho, and then the ratio would go up. It will go up to infinity, because if you have an infinite number of funds, then basically you will just focus on the family performance. Individual performance is acknowledgeable. Therefore, the ratio just go to infinity. Now, if you look at the effect of lambda, if we fix the rho to be 0.2, if you increase the lambda, that's the co-movement of the skill, then you see the ratio goes up, meaning that the sensitivity to the family performance becomes stronger and become more negative. And you see also this all depends on the number of funds, right? If the number of funds is large, then both effects get stronger. So these are all in closed form. We just plotted to visualize it. In a non-steady state, of course, things are more complicated. The initial covariance matrix, initial uncertainty matters, beta matters, right? Rho matters, omega f, omega I matters, and fund size, family size, and time matters, right? But the good news is that the main result, like the effect of the correlation, is still going to stay there. But one thing that is special is that if you are analyzing a non-steady state, then you don't need this ability to be time varying, because the uncertainty are there in a non-steady state. So this would be sufficient to generate positive common skill effect. So in the steady state, lambda has to be positive in order to have any positive spillover. In a non-steady state, you could have even lambda undefined, right? Because if the skill are constant, lambda is not defined, but you could still have positive spillover effect. Now, of course, we didn't really specify the initial belief, but you could think of this as like the covariance of the two unknown composite skill can be written down in this way, right? Based on your initial information set. It's clearly depending on beta and theta, valence of theta f, right? If the funds rely heavily on the family and you don't know much about the family skill, then the covariance of these two funds is going to be stronger, and this will generate a common skill effect. So these are graphs showing the sensitivities to the own performance and to the family performance over time. And here this is a constant scale case in which lambda is not defined. And you see you will still have the positive spillover or positive sensitivity to family performance if lambda is small, if rho is small, if the correlation in errors is small, right? If you increase the correlation in errors, this reduce the sensitivity of estimate to the family performance, but you don't, it just shows that you don't need to have a lambda in order to have the common skill effect. And sensitivity to the own performance, this doesn't seem to be so sensitive to rho, but it's positive and declining over time. Both sensitivity decline over time because you know more and you are not so uncertain, so you're not sensitive to signal. Now, for the mean reverting case, when the skills are mean reverting, we plot these sensitivities to the family, to the own performance, and to the they find that same result here. If you increase the correlation in skill, then the sensitivity to the own performance actually decline because you learn more from the other funds' performance, right? Now to the family performance, right, depending on your initial uncertainty and depending on the correlation in the error term, it can be negative or can be positive, but then it converged and settled down to some steady state level. And here, the same result holds, right? If there's no correlation in the co-movement of the skills, then it is positive family sensitivity to family performance will decline and converge to some negative level, right? And if the co-movement in a skill is strong, then we stay at a positive level. Okay, and then we, after derive these sensitivity metrics, and since we specify also the dependence of family performance on fund size, we can derive the endogenous fund size depending on investor belief about this composite skill of a particular fund. This is basically from Berkeley Green, and therefore you could see in our model the asset size growth rate is driven by the change in belief, and there's some convexity here, therefore in expectation is going to be positive, but nonlinear. So these are the predictions. These are the main theoretical results. So we want to have some implication, like simple test for the model's assumption and model's prediction. The assumption, the two main assumptions are as follows. First, there is a family component in fund's alpha generating skill. Second, the funds in the same family are subject to correlated shocks, right? These are two assumptions. All our result comes from there. And the prediction of the model is that the spillover effect would increase with the correlation of the change in true skills, and it will decrease with correlation of the shocks. And the impact of these two correlations on the spillover effect is going to increase in magnitude when the size of family increases. So we take these to the data. We take the standard CRISP mutual fund data from 1999 to 2009. Take the major equity fund category. Altogether, we have 2,300 funds from 600 families. And we compute the correlation of the errors using like standard factor model, and then take the residuals and compare all the pairwise correlations. And we also compare the, using like 3-month moving window to compare, to calculate the alphas. Then you get the time varying alpha. And of course, this time varying alpha is highly persistent because you use the overlapping observations. So we fit an AR1 regression model and take residual to compute the correlation of the alphas from this AR1 model. Residual of this AR1 model, use that as a proxy for the correlation of the time varying skills. And then the first test would be how does the family membership affect these correlations? And here I just bring this one table where it shows that you compare all the pairwise correlations, right? If the two funds in the same pair are having the same investment objective, they will have higher correlation. That's not very surprising. And also, if they are from the same family, it also have a very strong family effect. They are also more correlated. This is true for the correlation in errors, and it's also true for the correlations in alphas. And both effects seem to be quite strong, and no matter whether you use 3-factor model or 4-factor model. So we take this as evidence of a family effect in fund return, justifying our assumption of the model. To test the predictions, we need to compute some family characteristics, which measures, say, how how much correlation you have for a particular fund family. So for that, we just take all the funds in the same family, and then they compare the pairwise correlation, both in alpha and in errors, and take the simple average and use that as a proxy for the alpha correlation and error correlation for this particular family. Now, we look at then how does this correlation, which is now a family characteristic, affect the sensitivity of mutual fund flow to family performance and fund performance. And here's what we find. It's kind of surprising when we see this, also surprised, is that this is the, I just put this together in, two table, yeah. So in 2 page, is by same models, right? Different setup with different additional controls. We find that if your alpha is positive, of course you get more flows. And also if your family alpha is high, you also get more flow. So this, everything like alpha correlation, error correlation, they are all normalized by the sample median. So what you see here is a median effect. So like for a median fund, if family is performing well, this will help a member fund to bring in additional flows. And what's more interesting from our perspective is that if you interact the lambda with alpha, with family alpha, these increase the sensitivity, right? Meaning that for families that has stronger skill correlation, the sensitivity to family performance is stronger. But if they have stronger error correlation, then the sensitivity to family performance is weaker. So this actually drive down the sensitivity to family performance. And our theory would also predict that these two correlations, their effect on the sensitivity to family performance would depend on the fund size. If the size of family is big, these patterns should be stronger. So we add a further interaction term, right? That's the number of funds, logarithm of the number of funds in a family. And we should expect, according to our theory, that we should expect if the number of funds is bigger, and then the lambda effect on sensitivity to alpha should be stronger. And this also show up here in a significant positive coefficient of this three-term interaction term. And we also see some age effect, right? If this is fairly standard in a learning model, when funds become older, sensitivity to performance weaker. So to summarize, we hope to convince you that family performance is indeed very important when it comes to measure the performance of ability of a particular fund. And the effect can go in either direction, right? Overall effect can be either positive or negative, depending on the correlation structure. If the correlation of the skill are stronger than the correlation of noise, then the overall effect should be positive. Otherwise, it should be negative. And our theory also demonstrates that this pattern should be stronger for bigger families. And empirical evidence, we do show there is some family effect in fund returns, and there is some empirical evidence about cross-fund learning for funds within the same family. And we think our theoretical framework may be useful for some other analyzing some other issues as well, like whenever you have both common fundamentals and common noise effect, you may have a model that can consider both effects in one framework. For example, if you want to analyze the stocks in the same industry, or analyze funds within the same investment style, or countries in a neighboring region, presumably both effect would also be there. Okay, thank you for your attention. That's what I have to say.